video covers Griffiths E&M section 3.2.3, force and energy in the context of the image charge problem. Okay, so previously we have been discussing what happens when I have an infinitely conducting plane that's grounded in the xy plane, and we have a charge plus q that is a distance d away. All right, the goal previously was to find the potential in all space above the plane. And we found out that if we could find any solution, it would be the solution. And using the image charge problem, we said, all right, we must be able to pretend like there is a negative charge, an equal distance below the xy plane. That gave us our potential. We used that potential to find out the surface charge density on our conducting plane and the total charge on the conducting plane. And now the question will become, what force does our charge feel? All right, well, we have our image charge problem, so we can start with that. We have our force being equal to the Q of that charge times the electric field that it sits in. It sits in an electric field that comes from our image charge. So that is Q times 1 over 4 pi epsilon naught minus Q over the distance squared, which is 2d squared, gives us minus q squared over 4 pi epsilon naught 1 over 4 d squared, and the direction is going to be in the z hat. Right. At this point, the field line points along the z-axis. We have a negative sign out front here to get the directionality correct, but the field is generally in the z-axis. Okay. Oh, we use the method of images to also calculate what the force that our charge feels. Now, how much energy is associated with that configuration? We have a handful of ways that we can calculate the energy of a configuration. Let's start with one where we calculate the minimum work that's required to build that configuration. So I start with my conducting plane. There's no charges on it. Then what I want to do is I want to bring in my charge from infinitely far away and place it at a point D. So start out at infinity, end at D, dot the force that it feels with the path that it takes. Okay, I'm going to keep that integral right there. The force that it feels is minus q squared over 4 pi epsilon naught 1 over 4. Now instead of saying d, because it's not always at a position d, it's at a position generally of z, 4z squared, z hat, dotted with the path that I take. Well, the path that I take is going to be, negative dz in the z hat. Right, that's the easiest path that I can think of. Just follow along the z-axis all the way down. Okay, now I'm left with the integral of infinity to d, q squared, 4 pi epsilon naught, 1 over 4 z squared, dz. You do that integral, you get minus 1 over 4 pi epsilon naught, q squared over 4 d. Great. That's the minimum work required to build that, so that's the energy of our configuration. Now we have other ways we can calculate the energy of a configuration. Let's go ahead and borrow the potential expression, where this is equation 2.4.2, where I take the sum over all the charges in my system multiply that charge times the potential that that charge feels. Okay, let's try that. So I have two components of my sum. The first is the top. I'll pick the real charge, so that's a charge Q. It sits in a potential of generated by the bottom charge, 1 over 4 pi epsilon naught, minus Q over the distance, which is 2d. Then I have the next contribution, which is the negative charge, sitting in the potential generated by the other charge, my real charge, 1 over 4 pi epsilon naught, times Q over 2d. I'm left with minus 1 over 4 pi epsilon naught Q squared over 2d. But those are not the same. Why aren't they the same? I have the equivalent ways of calculating things. I use the force generated from my image charges, my image charge solution. I then use the potential from my image charge solution, which we decided was the correct thing to do. But they're not the same. They're off by a factor of 2. Okay. Now, why would that be the case? Why would it be off by a factor of 2? Okay. Let's borrow from our third strategy of calculating the energy of a configuration. I can go ahead and say that the energy is epsilon naught over 2 times E squared d tau, where d tau is all space. But if I were to rely heavily on my analogy of the image charge solution, I have a charge here, I have a charge here, and I'd have to integrate over, say, spherical coordinates here. We have to go theta goes from 0 to pi, phi goes from 0 to 2 pi, and r goes from 0 to infinity. But in reality, we only have a solution that's valid in the region of space above the xy plane. So only for z greater than 0, right? Probably shouldn't have picked spherical coordinates for this argument, but now I have theta that only goes from 0 to pi over 2. Zero to 2 pi, 0 to infinity. Right. So that's where that factor of 2, it's half of your full region of space. I could probably illustrate that better in Cartesian coordinates if I were to think about looking down the x-axis. Instead of integrating over all of my space, I only integrate over half of my space because my solution is not valid outside of that half. Okay, so while the image charge solution is a good way to calculate what the potential is, we have to be careful about the settings in which that is applicable.